Very good. Welcome back. In this second part of the lecture, I would like to study a little bit more about why it is that the statistical approach to thermodynamics works so well. This is basically going to be related to the thermodynamic limit, which is the limit in which the number of particles becomes large. So the question of why thermodynamics works so well, why statistical mechanics works so well, in part has to do with the kind of questions that you ask. For most of the questions that you could possibly ask, you get lousy answers. You have 10 to the 23 particles, and so you could ask 10 to the 23 questions. For most of them, you're just going to get nonsense. You have a container and you ask what is the position of a particular molecule, and what maximum entropy is going to tell you is it's the center, that's expected position with a huge variance, namely anywhere within the container. Well, you do not need a sophisticated, fancy statistical theory to tell you that. On the other hand, if you're going to ask questions about what's the temperature of this object given that it has this much energy, or is this system going to be in thermal equilibrium with that, or what's the pressure for these particular conditions? If you're going to ask questions that are the questions that are typically asked within thermodynamics, then you get remarkably good answers. And it's a good idea to try to figure out why that is so. In the process of figuring out why that works, you may also get hints about where it is that it will not work so well. So what I would like to do is explore an example of maximum entropy, statistical mechanics, and in the particular case I want to do is a simple case, thermal equilibrium with a single variable. The constraint is going to be something like the expected value of the energy is something like that. And what we would like to be able to show is that most of the microstates, you can figure out the probability of all of the microstates, but it is a good idea to classify the microstates as typical or atypical. And so there is going to be a region in phase space of typical microstates. By the way, typical does not mean high probability. If there are too few of them, you don't particularly care about them, even if they're highly probable. So we will discuss what typical means. It's an amazingly wonderful technical concept. The region of the of these typical microstates is going to be a region. So let's call it R. And if you integrate the region, this is the typical. So the typical region, integrate over the typical R region. You're going to have a volume. And one of the things that we're going to find out is that the entropy is very approximately equal to K, the log of the volume of this typical region. The mathematical formulation of the theorems we're going to discuss now, that goes back to Shannon and Weaver. This is 1948, 1949. And the person who actually, they did it in the context of communication theory. And the person who did it extended those theorems to statistical mechanics was James. Ed James did this around 1965. We're going to have occasion to actually read that paper in full glorious detail, or rather, I'm not going to read it. You are, as one of the homework problems, because this is a remarkably good paper. It's very, very much worth reading. So what we're going to discuss is the asymptotic equipartition theorem. So what we have is we have a system in equilibrium. The distribution of probabilities is given by the Boltzmann distribution. Z refers to the point in phase space. And the entropy is beta E plus log Z, and this is the Gibbs entropy. I'm going to divide by the K, which is the Clausius entropy. I'm going to divide by the K. So this is really the information entropy. This is the quantity that's going to appear in all the formulas. So that's why that's useful. So what the theorem says is the following. If the limit of the variance of the energy fluctuations, the standard deviation of fluctuations, divided by n, when n goes to infinity, this is equal to 0, then, okay, let's look at, we're going to be looking at what happens for large n. That's why this is called the asymptotic equipartition theorem, n going to infinity. So here we have the standard deviation for the energy. The square of this is the variance. The standard deviation for the energy, in many cases, is going to be connected, it's going to go like n to the square root of, to the power 1/2. So it goes like the square root of n. So if this goes like the square root of n divided by n, you clearly see that this is 0, okay? So if the energy fluctuations, the relative energy fluctuations goes to 0 as n goes to infinity, then as n goes to infinity, the quantity minus 1 over n, the log of f, tends to the entropy per particle in probability. This is important. In probability. This quantity tends to that in probability, meaning the probability that, we're going to write it down, the probability that this quantity differs from that by a small amount goes to 0. It just, the probabilities go to 0. So what does this mean? The important thing here the important thing here is that the right-hand side is independent of z. Therefore, what is going on here is that all the states, the probability f of z when you take the log, divide by n, blah, 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 all of this quantity here is going to go to the same limit independent of z. And this is what is referred as the equipartition theorem. You have a certain amount of probability, probability 1, total amount of probability, probability 1, and you have to allocate it among different microstates. Well, what this is telling you is that in the limit of large n, essentially all the microstates that are accessible, the typical ones, are going to have the same probability. So let me write that in English. The probability of the accessible microstates is roughly independent, the same for all. Roughly, the probability of the the probabilities are roughly equal. Now, the roughly is tricky, and the accessible too, right? You see, if the energy of the microstate is just too high, then there is no probability. So that's not an accessible macrostate. On the other hand, if the energy is very low, that's the highest probability state, very low. But there are very few states with high probability. The vacuum, energy is 0, there is only one state. So it doesn't really contribute much to the whole, to all the averages, right? States with very large energy don't contribute because they don't have any probability. States with very low energy don't contribute because they have a low probability, but there are too few of them. So that's what the accessible really means. And then what happens to this? They're roughly equal. The roughly refers to the fact that, do you see here that this is divided by n? So typically an entropy is going to be an extensive quantity proportional to n. So that means that somehow this quantity is going to be also, the log is going to be like proportional to n, roughly, okay? But imagine that this guy here, the log f, differs from s by something like the square root of n. Then clearly in the limit in which n is going to infinity, that difference, square root of n, can be, is going to be killed by the 1 over n here. And yet the difference between log f and s is still going to be huge. Instead of 10 to the 23, you might have 10 to the 12 difference. The log of f differs from s by a factor of 10 to the 12. You say, wow, that's huge. Not when you divide by the 10 to the 23. Okay? Very good. So how do we prove this, this theorem? So here's the proof. You go back to the Chebyshev inequality. That we used a long time ago, in chapter 2, which says the following: the probability that a quantity differs from the expected value by a quantity that's bigger than a delta is less than the variance, the standard deviation of that quantity, divided by the delta squared. So that's what we need. And what we're going to do is we're going to take the quantity x to be the quantity that we were talking about, 1 over n, the log of f. Why is this an interesting quantity to consider? Because the expected value of x is going to be 1 over n minus the expected value, right? Minus f log f integrate. So that's an entropy. So this guy here is going to be the entropy. And we can now write the entropy from this expression here, we're going to write it as 1 over n beta e plus log z. Very good. So we have this guy under control. We have the x, it's here. We have the expected value of x, it's there. So now we have to compute the variance. So next, the variance. The variance is going to be the delta x squared, which is going to be the expected value of x squared minus the expected value of x squared. So let's compute the expected value of x squared. This is going to be, we need, let me see, for this guy here, we need to do the expected value of this. So it's going to be 1 over n squared, the expected value of log f squared. And we have an expression for log f. It's going to be beta e plus log z. That's just the Boltzmann distribution, the exponent of the Boltzmann distribution minus beta e. And then there is the normalization factor. And then all of these guys have minus signs, but we are squaring. And so this turns out to be 1 over n squared beta squared expected value of the energy squared plus 2 beta the expected value of the energy multiplied by log z plus log z squared. And I think that's it. Very good. So that's this piece. Now, next we subtract this guy squared. And you see what's going to happen, right? When you take this guy squared, the log z squared cancels that. The beta e squared with the difference that gives you a variance, and the double product between the two cancels that. So when we do the calculation, calculate, right? Then the variance of x squared is going to be given by the following amazing expression, beta squared, n squared, and then you have the energy squared minus the expected value of the energy squared, which is the variance. How do we write this? Yes, beta, let's write it just as beta, the standard deviation of the energy divided by n all squared. So now we substitute, and we get substitute back into the Chebyshev expression. We substitute x, we substitute the expected value of x, which is just the entropy divided by n, and we substitute the variance there. And so the result is that the probability of minus 1 over n log f of z, this is x, minus the expected value of x. The probability that this quantity differs from this guy differs from the entropy divided by n by a quantity bigger than the delta is going to be less than there was the variance there, which was beta squared variance squared all divided by n squared, and then there was a delta squared. Now the theorem said if the limit of the standard deviation of the energy divided by n as n goes to infinity goes to 0, in other words, whenever the standard deviation of the energy is something like the square root of n or something like that, and this goes to 0, then you see what happens on this right-hand side, and we get our theorem that says that the probability minus 1 over n, the log of fz, minus s over n is bigger than delta is 0 in the limit as n goes to infinity. There you have the asymptotic equipartition theorem, which what it's saying is precisely what we have down here. This quantity tends to the entropy divided by n in probability. So when is it that we have this condition here? For example, when delta, the dispersion, the standard deviation of the energy, is something that goes like n to the 1/2, which is the typically what you have when systems are independent particles. What that means, if the system is big enough, then the particles over here are independent from the particles over there, so you can really increase the number of particles. They start behaving like independently of each other. That's what that ends up meaning. So now we can analyze this a little bit better. And we're going to analyze this by discussing the so-called theorem of typical microstates. So we're not going to prove it. I'll leave you to prove the theorem of typical microstates for homework. So, but the idea is we're going to define definition. The typical region. The typical region is going to be defined as follows. So the typical region R delta is going to be defined as being those states, those microstates, that have a probability that goes between, look at this expression here, log f, and this is s, between es and es. Let me give you the delta now. Minus, so this is minus, yes, minus es. Minus n delta plus n delta. Now, what we have in mind for this delta here, remember, this has like, this is the limit of large n, right? So n is like 10 to the 23 particles. By delta, what we have in mind is something, a quantity that may be very small, 10 to the minus 6. Notice that it gets multiplied by a 10 to the 23, right? So this number can still be very large, right? 10 to the minus 6, 10 to the minus 12. So delta is microscopically large, in the sense that this is still much, much bigger than 10 to the minus 23, right? But it's also much less than 1. So the delta is macroscopically small. So this is what we mean when we say that the thermodynamic fluctuations are actually very tiny. Compared to the 10 to the 23, They're absolutely small, but of course things are fluctuating all over the place there. That's the kind of thing here. Okay, this is what defines the typical region. And very good. We can actually simplify this a little bit more because we know that S is beta E minus or plus log Z. So what we're going to rewrite this S here is as being 1 over Z E minus beta expected energy minus N delta minus beta plus N delta. Now, notice what we're doing here. The left-hand side and the right-hand side do not depend on Z. So basically, all these microstates that lie in the typical region, they have essentially the same probability in the sense that the delta is very small. Essentially, remember when I said roughly, right? Okay, it can still differ by a whole lot, but compared to the actual value minus S, this N delta here is completely negligible, right? 1 part in a million, 1 part in 10 to the 12. Very good. So what does the theorem say here? Okay, this last expression is actually interesting because it says, look, wouldn't you expect the F? But F is E minus beta E divided by Z. And this is the guy that goes minus beta expected energy over Z, E minus beta expected energy over Z, and then you have a minus N delta and a plus N delta. So what this is telling you is that the EZ that we have there is something that goes between what you have over there and what you have over there. So the energy of these typical microstates is going to be the energy of the expected energy plus or minus nkt, some typical energy, multiplied by a delta, something like that. It tells you, indeed, the energies of the microstates are very close to the expected energy, plus or minus a small quantity. So here comes the theorem of typical microstates. The theorem says the following: for n sufficiently large, we have A, the probability of the typical region is bigger than 1 minus delta. What does this mean? We defined the typical region here by giving a lower bound on the probability and an upper bound. The upper bound is going to exclude those states that have too much energy and therefore low probability. And the other one is going to say, well, if this has too little energy, then there are too few of them. So here we go. The probability of that region is as small as you want. The delta here can be, well, within these limits, right? Microscopically large and macroscopically small. The probability of that region is 1 minus 10 to the minus 12, right? Really close to 1. All the states that are accessible are the typical ones, or the only ones that are accessible are the typical ones. B, the volume of that region, which is what we call the W, this is going to be E less than S plus N delta. So the volume is less than this amount, and it is also, let's write it like this, W is going to have to be bigger than 1 minus delta, a small correction, S minus N delta. So what this means is that the W is between e to the S and e to the S with a small correction, right? So S is the log of W with a small correction. So this is the kind of thing that's telling you it's a Boltzmann formula, right? The entropy is given by the log of the accessible part of the phase space, of the accessible volume of phase space. And finally, for CD, the last is that the limit as n goes to infinity of the log of W. This is making the previous statement a little bit more rigorous. The log W minus S divided by N is 0. In other words, whatever you have here between the difference between those two guys here, it's not quite equal to this, but if you divide by N, it goes to 0. So this is the proper expression here is that this is something like that. Very good. So what does this mean? It means that the typical region has probability 1. Typical states have essentially, roughly, the same probability. That's equipartition, right? It comes from up here. The typical states have this probability, which is contained between this and that, and the delta can be as small as you want. So basically, they all have the same probability. And what else? The phase volume W is e to the S, so that S is the log of W. Very good. So this is why the thermodynamic limit ends up working so well. Fluctuations in the large N limit, fluctuations end up being increasingly irrelevant. Thank you. See you next time. What we're going to do next time is we're going to put some of this stuff to good use, and we're going to discuss the second law of thermodynamics. See you next time.